Hello, Python programmers. Let's talk about NumPy. Numeric Python, a library built to facilitate the processing of data and improve on the speed of the built-in list data type. It's faster than a list because it's implemented in C, meaning that we have a Python interpreter, and part of that interpreter, or part of the NumPy library, is written in C. Does that affect us directly? No, but it's an interesting feature of Python. It's also faster because a NumPy array is required to be homogeneous. Therefore, there isn't a lot of data typing going on as the array is processed. The library knows that you have an array of numeric values, and it doesn't have to do type conversions or any kind of other things to facilitate processing. In the literature, we often see the word axis, and we can substitute dimension if we're familiar with how arrays are manipulated. So a multi-dimensional NumPy array is also a multi-axis NumPy array. And I don't think this version number is current. If we type np dot underscore underscore version underscore underscore in our Python interpreter shell, we can see the current version that we have installed of the NumPy library. And we also have to install that library. I hope that goes well for you. I installed mine using the Windows command line, and I typed pip space install space NumPy. You'll know right away if you don't have it installed, because if you try to execute the import statement, you'll get an error, module not found. And then once you've got the installation completed, you'll be able to run that import command. And this also applies in Eclipse. Make sure that you add that import statement to any Eclipse module that you write that will be using NumPy library methods and functions and classes. So let's see what version I have. Oh, my fault. I forgot the as. So NP is an alias that most Python developers use to refer to the NumPy library. You don't have to do that, but it shortens up the coding a little bit. It's a few less keystrokes when you use the library, and everybody recognizes that as NumPy. So I revised my import statement, import NumPy as NP, and let's try that version command again. Okay, I have 1.21.1, and you can see when I created the slide, probably last year, it was 1.17.4. You probably have something in between those two numbers, which is fine. It doesn't have to be the exact version I'm using. I know mine is the most current because I installed it very recently. So generally, we're going to have homogeneous arrays of integer values or floating point numbers. And as I mentioned a moment ago, and I kind of get a kick out of this because Python is an interpreted language, and those languages are generally slower than compiled languages. Therefore, to make Python faster, they implemented a little bit of C. They implemented a compiled language into their interpreted language. And they got a dramatic speed increase by doing this, and everything worked out fine. It's just an interesting adaptation of a much older language, C, which was designed to be fast and small, and Python leverages that to make their interpreted language run faster. Now, I created a benchmark just to demonstrate that, yes, there is a speed increase. And I'll show that to you now. I'm not saying that this is authoritative by any means. It's a very simple benchmark, and I didn't go into any depth of thought as far as what lists can do and what NumPy arrays can do. But it does show you that in this very simple case, there is a dramatic speed increase. And as you can see, I imported NumPy and aliased it to NP, the way most developers do. And I have another two import statements here that I use to time the program. So those are not directly related to NumPy. Those are just for timing purposes of the benchmark. My benchmark is to take a 1 million element NumPy array and a 1 million element native Python list and do some simple processing against each of those and see which one is faster, or if either is faster. My processing consists of multiplying each element in the array by 2, just doubling each value and storing that in a new data structure. So the original data structure, whether it's the list or the NumPy array, does not change, but I end up with a second list or a second NumPy array. And the timing logic is wrapped around that. I'm not going to spend any time on how I did the timing. I basically Googled how do I time a Python program and found some reasonable solutions and implemented one of those, but that's really not part of this issue. I ran each test 100 times just to possibly normalize some computing delays. The machine is doing a lot of things in the background, and a file operation or an internet operation or an antivirus update, anything in the background could cause the test that I'm running to be delayed. So if I run it 100 times, that kind of smooths out any possible delays that might have occurred if I ran it only once. And relatively speaking, if I run both of them 100 times, it doesn't matter that I ran them 100 times. Okay, when I run this, I get 0.219 seconds for the NumPy test, and I get 8.7 seconds for the list test. And that's a dramatic difference between the two. If I divide 8700 by 219, it's 39 times faster to do that processing in a NumPy array than it is a list. And I can run this again and get slightly different results, but the trend is certainly towards the faster processing being in the NumPy strategy. So this is just a way to think about the difference between the two and visualize what happens when you create a little test. I'm not going to ask you to do this. I wanted to just introduce you to the dramatic difference in this case between those two data structures. And I will post this code on Canvas, and you're welcome to grab it and look at it. And if you'd like to enhance it, or if you find anything that could be improved, let me know. Remember that import statement? It's just a mistake that I make often, is to start writing a project and begin referencing a library that I haven't imported yet. So I like to emphasize that. In this example, I was attempting to create an array and then reshape it into 2 dimensions, and that failed because it didn't know what NP was, and then I remembered to go back and add that import statement. So let's do that in our shell. Copying that right from the slide, np dot, I'll just give it a name. You can see that it created a 2-dimensional array, 4 rows, 5 columns. It initialized the values from 0 to 19, so I have a total of 20 elements. If I try to do this with too many elements, you can see there I'm asking for a 4 by 5 2-dimensional array, but I'm providing 21 elements. 4 times 5 is 20. There's going to be an element left over. It doesn't like that. If I provide too many elements, what if I don't provide enough elements? Same thing. And we see then that we can call reshape to build a 2-dimensional array from a 1-dimensional array, but we have to make sure that the parameters match. The syntax is very similar to what we've already seen with lists. And we've seen in the past we can do lists of lists. So I've got, in this second example, a list of 1, 2, 3, 4, 5 because it's in square brackets, meaning we know it's a list. And then separated by a comma is another list of 5 elements. And that's fine. Those are 2 individual arrays. But if I want to pass that to a NumPy function to create a NumPy array, I need to make that into a tuple, and then it knows how to process that. Then I put parentheses around the whole thing, and you should be able to recognize that looking at the delimiters that I used as a list separated by a comma from another list, and then all built into a tuple because of the enclosing parentheses. And in this example, I illustrated what I tried to do on the previous slide. It's going to fail in the first case because I'm passing it 2 separate lists, and the syntax of the array function just doesn't know what to do with that. In the second example, I got my ducks in a row, and I wrapped each of those lists together into a tuple by adding another set of parentheses, and then the array function was fine with that. So let's take the second one, since we know the first one doesn't work, and go back to our shell again. And we can print out the value. Remember that in this Python shell, this REPL environment, I can just type the name of a variable and have it print the variable. And in Eclipse, I'm conditioned to use print, just a slightly different syntax, but they both work in this environment. Let's try this with a non-homogeneous set of values. I just replaced the numeric 8 in that second list with a string by putting quotes around the 8. The command is accepted by the interpreter. I don't get any error message back. What's it going to give us? You can see what it did was it looked at each individual element in both lists, and it had to make a decision. It decided to convert all the elements to characters. Remember, it's got to be a homogeneous array. So since one of the elements was not like the others, it converted all of them to strings. And that's perfectly okay if you understand what's going on, but it can be very confusing if you don't know what happened. It's interesting that it didn't convert the 8 to an integer because all of the other values were integers. And the thought process there is that it's possible to convert anything to a string, but it's not possible to convert any string to a numeric value because it may not be convertible. For example, if I just put an x in there, you can see there that x can't be converted to an integer. So instead of going down that road and possibly having a runtime error or some kind of data conversion issue, Python simply elects to convert all of them to strings. Once we've got an array, we can use the shape method to display what NumPy is using to represent that array. In this example, I created an array of 20, as I did earlier, and I reshaped it to a 4x5 two-dimensional array. And then I simply used the shape method to print out what that shape is, and you can see that it's 4x5. As we learned with lists and tuples and dictionaries, arrays are zero-based when we index. The first element is index 0. And we emphasize this because it's confusing to non-programmers. So in this case, if I print my array sub1, sub2, I'm asking for the second row and the third column because we're zero-based, and I'm going to get the 7 in the second row, third column. And this is a very convenient way to do multi-dimensional indexing simply by adding values separated by square brackets to that name of that array. We've kind of abandoned here, and it's a little confusing to me, we've kind of abandoned what we thought the square brackets meant a few minutes ago. A few minutes ago, a square bracket meant we were in a list, but in this syntax, a square bracket means we are indexing into that data structure. And we pronounce this myArray sub1, sub2, myArray subscript 1, subscript 2. And we can even get more creative by using commas. In this example, I created a 3-row, 3-column array, and I went ahead and used the int32 argument to tell NumPy to resist the urge to make these into floating point numbers. So I'm simply forcing NumPy to use int32 or integer data types in these array elements. And then when I want to slice into that, take a look at the syntax here. I'm saying myArray square bracket 0:2, comma 2. And you can reverse engineer the output of that. You can see that I got a 3 and a 6. Where did the 3 and the 6 come from? Well, the 3 is the first row, third column, and the 6 is the second row, third column. That means 0 colon 2 gives me what? Take a moment to think about what the 0 colon 2 maps into, and take a moment to think about what the 2 maps into. So be sure that you can interpret that syntax. The colons, the commas, the square brackets all work together to let you slice into that array in all kinds of different ways. Have you got it figured out? The 0 colon 2 means I want the first row and the second row. Remember, the zero-based indexing means the first row is row 0, and the 2 on the other side of that colon is an exclusive upper bound. We're not asking for 3 rows, we're just asking for 2 rows, the 0th row and the 1 row, if you think about it that way, or the first 2 rows, whatever works for you. And then the column that I'm after follows the comma. I'm after column 2, and since we're 0-based, that's the third column in the array. Therefore, I get 3 and 6. Now it's displayed as it looks like a row because of the square brackets. Another thing that would be interesting is to try this example, but print out the type that I'm actually getting. I find it's very helpful to me when I do expressions on NumPy arrays and pandas arrays to print the data types, and I can relate to these things a lot more. So I would take the time to enter this code into your interpreter, and after you print out my array bracket 0 colon 2 comma 2 bracket blah blah blah, print out the data type of that and see what you get. Do you get a NumPy array? Do you get a plain old list? Do you get something unexpected? That will help you to get a better grasp on the slicing operation that's going on here. Here's the code from the slide. We used the array function to create a NumPy array. Then we demonstrated our slice, giving us the third column in the first and second rows. And then what I'd asked you to do was print the data type of that slice. And you can see that the slice results in another NumPy array. I'm also curious about the shape of that. Let's print out the shape of it. And that's not the correct way to print out shape. It's not as simple as the type function that we just did. So let's go back to the slides again and find an example of shape. And it's actually a property of that object rather than calling a function. We need dot shape. So I need to go back here and dot shape, make sure I have my parens, whoops. Make sure I have all my parens, and do I need parens there? And I'm having problems figuring out how to get the shape of that thing that we sliced. So let's try another option. Let's take out these parens because we know they weren't supposed to be there. And let's put parens around the result of the slice. And it still doesn't like shape. All right, let's try another option, and I'm just going through the thought process here of trying to solve a problem like this. I'd like to know what the shape is of that thing that I sliced. So instead of just printing it, I am going to assign it to a variable. And then I have my 3 comma 6. And it actually tells me it's an array, but let's see if I can do a shape on it. Okay, there it is. It is a 2-dimensional array. So that took a little bit of doing, but hopefully that was an insight into the thought process that I might go through to try to figure this out. Sometimes I can do function chaining. Sometimes I can tack one function onto the end of another to get the result I need. Sometimes I have to break it up into parts. In this case, I broke it up into a slice and then assigning that slice to a brand new variable that I poofed into existence and then printing out the shape of that variable. Here's another slice example. Just like we used with lists and tuples, we can do negative number indexing, which looks very, very weird if you come from a C# background. In this case, we're going to get the last row of that thing that we created. So remembering back to a previous slide, we created a one-dimensional array of 20 elements, indexed or initialized from 0 to 19. We reshaped it into a two-dimensional array of 4 rows by 5 columns. We sliced it to get the very last row, which would be 15 through 19. Back to the slides. Slide 11. We are demonstrating how to do mathematical operations on entire slices of this NumPy array. And this is very powerful because we don't need to do loops. We don't have to write the for statement, the range. We don't care what the range is. We know that the NumPy library will figure out how to apply that mathematical operation across the entire slice. In this case, I've got my old faithful array, 20 elements in a two-dimensional 4-row, 5-column configuration. I print out the last row just to make sure that it is what I think it is. And then I multiply every element in that row by 42 simply by writing one line of code. And you can't do this in a lot of languages for different reasons. But in this case, all I have to do is tell it what I want to do and what the slice is, and it goes off and figures out what the loop boundaries are and applies that operation. So in one line of code without a loop, I'm able to increase an entire row by a factor of 42. Very powerful. The times equal, if you aren't familiar with that, I can rewrite it for you a different way. My array sub -1 equals my array sub -1 times 42. These two are the same. The times equal is simply a shorthand way of multiplying. That applies to all mathematical operations in Python and in C#. It's just a shorthand way of writing multiplication. And I expose you to it now because a lot of people use it. Therefore, it's something that you should see. If you don't want to use it in your code, that's fine. You can simply write it out more explicitly as I have here. But either way produces the same result. A little bit more slicing. And I expect you to be able to read this syntax. Separating the two dimensions by a comma. I'm asking for everything in the first dimension and only the third index in the second dimension. and make sure that you can read that and make sense out of it. The empty colon, that means I want all the rows. The 3, I only want column, physical column, or index 3, which is the physical fourth column in that. And then it displays that information to me because I put that in a print statement. We could just as easily have used that in an expression to do a mathematical operation on just that slice. Python programmers learn to think this way. So instead of writing one loop inside of another loop and ended up with a more complex expression, we can do this in one line of code. If I gave this job to a C# programmer, I would get back one loop inside of another loop. One loop to step through the array, the rows, and one loop to step through the columns. So I'd end up with probably 3, 4, 5 lines of code at least. But here, I can do it with the slice syntax. Very powerful. One more example, make sure you can make sense out of this. One mistake that I made quite often learning this material is that when I call reshape, it creates a brand new array. It doesn't change the original array. Therefore, I have to assign it to something. I've illustrated that for you here. I create my array. I reshape it to 6 rows and 2 columns. So I started out with 3, 3, 3, and 3, and I'm going to end up with 6 and 2. But I don't get what I think I'm going to get right away because all I did was call reshape, and I didn't assign the result of that reshape back to anything. So it did the reshape, and then it threw it away. And you can see that is illustrated here because when I print out the value of A, it's the original array that I started with. It's not reshaped. So you want to be careful when you call functions like reshape. Actually, it's a method, not a function. That you assign that to a variable or use it in an expression so you don't lose it. And again, let me just repeat what happened there. The reshape method consumed the value of A, which was an array. It reshaped it to 6 rows by 2 columns, and then it threw it away. Used up CPU time, you allocated memory. The only benefit we got from this, because we're in this REPL environment, is that it printed it to the console. But it's gone immediately after that. And I prove that by printing out the original array A, and you can see that it is unchanged. In the second snip here on the slide, I changed my thought process and I called reshape the same way, but I assigned the thing that reshape generated back to another variable, in this case called B, and then I printed B and I get what I wanted to get. I get a 2 column 6 row array. And notice also, even if you do this in Eclipse, there is not going to be a warning or an error generated. Eclipse is not going to tell you, Python is not going to tell you that, hey Bill, you called reshape and then you discarded the results of that reshape. That's not the kind of error that's generated. It would be nice. Sometimes we just feel better looping or iterating over rows or even columns. And here's an example of that. I create my old faithful two-dimensional array 4 by 5, and then I can use the for logic, which kind of looks like a loop, and it is. Each pass through the loop, it initializes this variable. I chose the name row to the next row in that data structure. Once I'm in that loop, then I can do things to the rows like print them out, add them to another data structure, write them to a file, whatever I need to do. We do have the capability then of iterating. And if you think back to a previous slide, I'm back to slide 11. I could do that iteration loop, that iterative process, to multiply values. Just like I did here without a loop, I could do that with a loop in slide 15. And this is what the thought process would be for most developers who have not worked with Python. If you're a C# person, if you're a Java person, even a C or C++ person, you might find yourself writing loops to do all these things when you don't necessarily have to. Here's my nested loop. The outer loop gets a row in the array. The inner loop gets the individual elements in that row. So again, I can accomplish the same thing different ways. That's true in all programming languages. It becomes even more evident in Python as you study it. There are just numerous ways to do the same thing. If I don't need to slice, I can actually perform a mathematical operation on every element in the entire array simply by using the array name in the expression. So let's grab this code off of the slide. Travel back to our REPL environment. And you can see how easy it is. And you can imagine, I'm not going to ask you to do it, you can imagine that I could have accomplished the same thing with nested loops. But with one line of code, I replaced two loops and I replaced a lot of opportunities for logic errors. This is a very useful feature when you're doing data processing. Sometimes you want to know what elements of an array meet a particular qualification or requirement. So in this case, I'd like to know what elements in my array are even. And a way I can compute evenness is to take the modulus of a number. And if the modulus of a number is 0, then that number is evenly divisible by 2, therefore it's an even number. So I'm creating a second array, and the second array is going to be the result of every element mod 2 equals 0. In other words, compute the element mod 2, what's the integer remainder of that element divided by 2, and then check and see if that value is 0. And an equal is the equality operator, and that generates a logical value of either true or false. I end up with an array that is nothing but trues and falses. And that tells me that the individual values in my original array, which was called my array, are either even or odd based on the true or false values in this new array. So there's a way to map the results of a mathematical operation into a brand new array. Very powerful. And as you might imagine, there are numerous built-in ways to process NumPy data structures, Amax. You can imagine there's an Amin and many, many, many more of those. As we've discussed, I encourage you to learn the basic syntax, learn how to put a program together, And then when you need the specifics of performing an operation on a data structure, Google is your friend. Sometimes we need random numbers when we're doing simulations or generating test data. This code illustrates how easy it is to create an array of random floating point numbers. The way that the rand function works is it generates a number between 0 and 1, exclusive of 1. And then you can use that rand function to populate an array. Given this little code snippet here, I'm curious about some things. Let's go back to our REPL and let's recreate a little bit of this code. So I have t equals np.random.rand99, t equals np.random.rand99. There's my t. Notice that I am using the NumPy library because I typed np.random. So this function, this capability that I'm exercising here, is built into the NumPy library. But I'd like to know exactly what I got. And as expected, it returned to me a NumPy array. That's terrific. Does it have a shape? Am I able to, ask for the shape of that? Well, it tells me it's a tuple. Interesting. You can verify that with the parentheses surrounding that entire data structure. So when I print it out, I see the parentheses there. What about a particular element of that shape, of that data structure? So t sub 0 is a tuple, but what exactly is t sub 0? Okay, that makes sense. And I'm illustrating then the value of curiosity and the value of experimenting to see what the data structures look like and how they're manipulated. If I print out t sub 0, 0.47282, I can look up at the very top, and as expected, that's the very first element in the array. If I print out t sub 99, there is no t sub 99. How about t sub 1? 0.0113. If I scroll up a little, there's 0.0113. How about t sub 98? 0.683. There it is right there. And the reason there was no 99, the reason that gave me an error, index out of bounds, is because when I created this thing, I told it to stop at 98. I told it to go from 0 to 98 and stop before it got to 99. Therefore, there is no 99. Here's something you're not going to see in other languages, many other languages. I can define an operation, and then I can use that operation against an entire data structure. I'm not going to get trues or falses in this case. I'm going to get the next step in that process. I'm only going to get the array elements that were labeled with true. I'm only going to get the array elements that are even. So I went from a 20 element array down to only the elements that were evenly divisible by 2. And that took me 2 lines of code. I did an assignment to temp, then I use that to generate a new array called evens. I can merge arrays. So here we are with an example of A having 3 rows and 5 columns. I print out the shape of A and I verify it's 3 by 5. I print out the size of A. There's a new function we haven't talked about, and I verify it's got 15 elements in it. And then I create another array called B. Now look what I did there. The whole array, the whole initializing data set is in parentheses, and the individual elements are in square brackets. So I end up with a 3 by 1. 3 rows, 1 column. And then I use slicing to put B into A, to overlay the B array into the A array. And the slice is A square bracket colon comma 0 colon 1 closing square bracket. And then I can assign that slice to B. And I'm being very careful here because the slice should be the same size as this source array B. So whatever I'm slicing better be 3 by 1. And then once I print out that result, I can see that the very first column has been replaced by the contents of B. So there's a powerful operation for perhaps doing image manipulation where you want to lay one image on top of another. All you need to do is create the correct slice and do an assignment operation. This is replacing nested loops and replacing indexes, which just are opportunities for error. There's the code from the previous slide. I encourage you to take a look at it, play around with it. Can you move the location of that assignment into another part of A? And that's the end of this slideshow. I do want to show you another Eclipse project, however. So this is an easy demonstration of importing from a CSV file into a NumPy data structure. And I provided this on Canvas. The file that we're interested in that contains our data is Sacramento Real Estate Transactions.csv. It's in the same folder as the main.py module. We can open it with Eclipse, but remember that it really isn't an Eclipse worksheet. It's a CSV file. All the formatting that you see here has been added by Eclipse. So if you click the Save button, you'll get this warning, and you have to go back and change the file type if you want it to become a workbook, which we don't. We don't need to do that. All we really care about is the convenience that Excel offers. So you can see there's a column heading row across the top, and there are text columns, and there are numeric columns. And I'm showing you this to point out something that you need to be aware of if you're going to do this kind of processing. This is more amenable to pandas, our topic next week. This is not something you probably want to do in NumPy, but again, it helps us think about how to solve problems, and it illustrates a shortcoming or an issue that you need to be aware of. So again, keep in the back of your mind that there are text columns and there are also numeric columns. There's also two types of numeric columns. There is a floating point, which has a decimal place, and there are integer numeric columns which do not have decimal places. And NumPy is aware of that. So I'm going to close this. I'm not going to save it certainly because I don't want to create a worksheet. And here's the code. Hopefully you've got a chance to grab it from Canvas. Getting it from the CSV file into a NumPy data structure is pretty easy. I call gen from text, and I would be pretty sure, I would be fairly comfortable in telling you that there are other ways to do this, knowing Python, but this is just one way to do it. Gen from text. The first argument is the file name. It doesn't need a path because I put it in the same directory as main.py. Since they're in the same directory, there doesn't have to be any kind of path name associated with that file. The delimiter is, since it's a true CSV, the delimiter is going to be a comma, and that's between columns. And then I do have a header row, therefore I say skip one row to not bring in the headers. And if you've done any pandas, which we will next week, you'll recognize that this can be handled also using pandas and probably more effectively and efficiently, but this is a good exercise for us to talk about right now. And I was playing around with this project. I shortened the data file just to do when I was doing some debugging, but I commented out that line of code. You can ignore that. And you can see that during the debugging, I wanted to print out what I was getting from the file. And since there were thousands and thousands of rows in the original file, that print statement got a little cumbersome until I shortened the file. And actually, let's go back up here and take this short off. That doesn't need to be there. And you're going to see that there's a lot of data here. Okay, so one line of code reads the file, creates a NumPy data set. We're off to the races. I print the shape of it because I'd like to know what I got, just to give myself a level of confidence that I am actually reading the file and getting what I think I'm getting. 985 rows, there aren't thousands and thousands, I misspoke. If you're still not comfortable, you can go back to Excel and you can verify that there are 985 rows. There they are right there. 986 counting the header row at the top, 985 not counting the header row. And then there's a print statement, but we'll comment that out in a moment. Okay, here's my slice. And I realized that since NumPy wants to process numbers, then I'm better off only grabbing the numbers. I don't have to do this, but I'll show you in a minute why it kind of makes sense. And my slice is, I want all of the rows, therefore I just put a colon in there in the first dimension, and I want only these columns, and I can create a list of columns, and the Python interpreter will slice that, which is pretty powerful again. You're looking at loops and nested loops and all kinds of processing and indices if you don't have this slicing capability. And then during my debugging, I wanted to know that I was getting what I indeed thought I was getting, so I put a print statement in there. I'm going to take that out because I don't want to print 900 rows. The next thing I did was use the max function to compute the maximum value across two of those columns, sale prices, and then also the minimums. Then I print those out just to see that I'm getting some information that's useful. And then this falls on its face. And I left it in here on purpose because I want to show you what happened when I read in the data, and you'll understand why I can't do this. Pandas, yes, this works great. NumPy, not so much. Notice also that I put all of this into a function called CSV demo, and then I call the function down here. The actual entry point for the code then is going to be line 54. When you click the run button, it starts at line 54, which causes it to jump up here and execute this function. Okay. I've only got 3 print statements. Looks good. Let's give it a shot. Click the run button. And there's my output. I got a minimum sale price, a maximum sale price, and a difference. Useful information. Same thing I could have gotten from Excel, but I've automated that process now. I don't have to open Excel, do a sort, do a mathematical computation. Python does all those things for me. It happened quickly. Pretty much when I clicked the run button, it loaded the file, did the calculations, printed them out. I processed 985 rows. Looks good. But I want to show you something that happened behind the scenes so you understand NumPy a little bit better. And what I could do to show you that is print the data, but that's 985 rows, and I don't want 985 rows in the console. It's just too much scrolling. Instead, I'm going to use the debugger, and you'll notice that I've already got a breakpoint here. Make it go away. I double click in the margin next to the line number, and I get the little green visual cue telling me that there's a breakpoint there. And then I'm going to run this in debug mode. Instead of clicking the green button, I click the bug. That begins to run. It's a little bit slower, but you can't tell. It goes to the first breakpoint. It stops. It highlights that line in green. That line is waiting to be executed. It has not executed line 13. It stopped waiting for me to tell it what to do. I'm not really interested in stepping through this because the logic is linear. There's no decisions being made. I'm not trying to figure out if I have a logic error. But something very powerful that I can do is hover. And I can hover over this NumPy data structure. And if I'm good with my mouse, I can make it bigger. Okay. And it's not the greatest. It doesn't automatically resize when I make the window bigger. But I know something about the data, and I can make sense of this. Take a look at this number here, 9583 by 10 to the 4th. Remember that number, 9583 by 10 to the 4th. Go back to Excel. There's that number, 95838. I'm sorry, I left an 8 out when I read it to you. 95838, my mistake. In the file, it's a zip code. When NumPy processed the data, it converted it to a floating point number. Okay? It's still a number, it's just in a different format. And it's still the same number too. It didn't change the value of the number. But look to the left of that. Okay? There's NAN. Now that, you may have already guessed, is what happened to the street. Because the street is not a number. It's a text string. And it cannot be converted to a number. So Python, since a NumPy data structure has to be homogeneous, made the decision to convert that to NaN. Your strings are gone, but they're replaced with NaN, which stands for not a number, which is actually a floating point value, NaN. So it's not a string, it's a placeholder for something that wants to be numeric but isn't really numeric. It stands for not a number. And it did that for all 985 columns. It's only showing me the first few. So that is a little trick that you need to be aware of when you're using gen from text. You're going to lose all of the non-numeric columns. They're going to be converted to NaNs. And there may be ways around that with gen from text. I haven't studied that method in great detail. You may be able to say make everything into a string. Don't make everything into a floating point number. Or I don't know, and certainly there are other CSV utilities you can use to do that. But since the array has to be homogeneous, the decision had to be made. Is everything going to be converted to a number, even the things that can't be numbers, or is everything going to be converted to a string? And gen from text makes a decision to convert everything to a number. And that's why in line 16 I went ahead and chopped out the things that I knew were not numbers because they had no value to me anymore. So you've seen a really useful, easy to configure function method to read from a CSV file into a NumPy array, and you've seen a brief introduction on how to do some calculations on that array.